All right, so today my objective here is just to cover our new document 334.1, the guide to concrete shell structures guide. So, the right way there. The ACI definition of a shell is a three-dimensional spatial structure made up of one or more flat or curved slabs whose thickness is small compared to other dimensions. So, in other words, we're using geometry to maximize our span of coverage while minimizing the materials used. And that's really what shells do. They cover the largest area with the smallest amount of material. So shells historically started coming into existence in the mid or to late 1800s, and they started with concrete water tanks. That was the very first shell structures. This is a railroad water tank from about 1900, and then they developed from there. And so we have to be grateful to the designers, and they were really just mathematicians that were also, many of them were contractors as well, because no one else would build these structures except for these people that felt like they understood them. And so they came up with the formulae and the methods to build some pretty amazing structures. And so this airship hangar, this is for the lighter than aircraft, your Zeppelins. And it was built in France around 1928. Is this picture. So as we think about that, we got to remember that computers in those days were people that just had a pencil and paper. Those were the computers. And so the shells that they were able to analyze had to be very simple per se, and they had a lot of math to do to get that done. And whereas today, our computing power is almost unlimited. And so we have maybe a construction issue would be what is lagging behind now. We can design way more things than can actually be built at this time. So with our new document, we describe shells in 10 different groups. And so the first group that we want to look at really quick, so we're just going to go quickly through these different shapes. So folded plates. These were really very popular following World War II for about 3.5 decades. They, very simple to form because they have nice straight edges, and so forming them was something that could be accomplished easily. They were certainly used a lot of material and shoring and different things to build these, but they could do these, and then they could span long distances with relatively thin slabs. The second group that we looked at are our shells of single curvature with a constant radius of curvature. So your silos or tank type structures. Or here's in Hershey, this is 1936, this was a concrete barrel shell roof. And this is one of the oldest barrel shells in the United States. So once again, fairly simple. I mean, the curvature is only one direction. It's easy to form with straight dimension lumber in the other direction because it's only curving one way. And then to get a little bit more complicated, we have single curvature with multiple radii curvature. So then you've got your elliptical arches or tunnels. They can be flattened tunnels or vertical tunnels. You see railroad tunnels like that. And so once again, long, straight in one direction, but curved with various radii in the other direction. Our fourth group is double curvature with a single radius. So these are what we call synclastic shells because they're doubly curved in the same direction. So they're curved this way, and it's all uniform. So your concrete dome is going to fall into this, or your dome shape. These are different. So we've got a hemisphere here. This is for storage. This is a cement storage facility. You've got a water tank with. It's just got a dome cap on it. It's just the very cap of the dome. And there's an office building there. So they are all single radius of curvature though. So there's the next one is a little bit more complicated. We're going to have multiple radii of curvature. So then once again, your eggshell digesters. They're elliptical in plan view or section or both. So depending on the forming method, if you're going to use hard forms, and cast concrete on top of them, these are very hard to build because you've got to change the dimensions at every single place. But if you're going to do something like an airform, which we use a lot now in the dome world, then they're not really much different than a hemisphere. I mean, it's just, yeah, it's kind of the same. It is a little bit more difficult, and you don't see as many of these. You see, the most common shell that we see today is the dome shape. And then, so this is our double curvature with curvature in the opposite direction. So we've got a water tower, a cooling tower, and a hyperbolic paraboloid. And so they're anti-classic shells, so they curve, in one direction and then opposite, in the other way. And the cool thing about the hypars as well is that they're straight lines. Okay, it's a straight line, and it stays straight as it curves across, and that creates the double curved surface. And so that they're really a cool thing that they figured out how to build and design. So now you've got your freeform shells. These are the unicorns of the shell world. They don't have to have any geometric formula that they have to follow. They can just float around. The designer can come up with. Usually the designer is marginally sane. He or she is just willy-nilly, right? But they're cool in that they can, and we have the technology to be able to do these. These are both happening in Japan, and one's a museum, one's a funeral home. And so a difficult thing about these is that you have to describe and have the geometry nailed down to be able to analyze and construct them. And so that can be difficult with a freeform shell, because how do you say where exactly the curvature is, and if there's no certain point where the radius starts? And so these are a lot less common, and a lot more.
I've also seen the roofs on train stations and bus terminals with those freeform canopy type things.
Yeah, you can. Yeah, there are more around. Yeah. So. Then we have form-found shells. Now these sound a lot like freeform, but the difference here is that generally you've got some points. So like for this bridge, you've got some points down here where the boundary conditions, where you have to have the boundaries. You've got a highway or a river here, so you can't have, so you've got to have your boundary conditions here, and then you've got to support the bridge deck here. And then the neat thing about these type of shells is that once you have these constraints where they need to stop, well then they can play with the geometry so that the principal stresses inside the shell are all membrane forces. They're all pure axial tension or compression. And so very little bending exists in these shells because of the way they have found the form to just follow those stress lines. And so that's a really cool thing about them. Grid shell. So this is, think Pierluigi Nervi. If those of you who were at the last session that we had, or the last ACI convention here in Philadelphia, was in 2016. We had an exhibit on Pierluigi Nervi. He was a Italian designer. It did a lot of things in Rome, and so he made these shells based on a series of beams that interconnected. And this is the Piazza dello Sport in Rome. It was made for the Olympics. And so really you have lots of different beam elements that come together and form a shell. These are dome-type structures. And then our group 10 is just the combined shell. So you take a piece from one, a piece from another, and you whack them together, and you have just different combinations of all of these types of shells. So that's how we kind of describe the shells. Then as we get into analyzation, there's really two ways that we analyze shell structures. There's a closed form solution and a numeric analysis, or an FEA, or things like that, right? So the closed form analysis, this is the one that the mathematicians came up with so many years ago, and there's a limited number of shapes that they derived equations for. Now these equations are derived from the theory of elasticity and based on the flexibility assumptions, okay? And so so we get some formulas that have been derived, and it's just the same as if you were to design like a beam or a column by hand with equations. Those are based on the flexibility formula. So when we have these shapes, this one's for a dome shape here, and you can see the so this comes out of Dr. Arnold Wilson's book, Practical Design of Concrete Shells. But the procedure for the closed form analysis is you start with membrane stresses. So you have your shell, and you put loading on it, whether it's external live loading or whether it's the dead load of the shell or the other loading that you put on it, and it resolves that loading into membrane forces. So there's not really any bending. It's just there are compressive and tensile forces in the shell. But then there's some errors with that, and so you have to start with that analysis, and you design it, you analyze it for in a number of points that you got, and then you go into your errors. So your errors are edge conditions, edge constraints, deflections, and you analyze it for the errors, and then you have compatibility, or you have to resolve those errors, and so you have some external forces that you have to apply to resolve those errors. And then you basically superimpose all of those different analyses on together, and that gives you all of the different bending forces and the axial tension and the axial compression, and all told through there. So the downside of closed form analyses are that there's a limited number of shapes. Domes are constant curvature. Some domes that are elliptical in plan or in section. Barrel shells, folded plates, lots of those have these closed form solutions. But your many things, if you're dreaming up something, a combined shell, you're not going to have a closed form solution because the geometry is just too much for that math that had to be done to put it together. So then you've got your numeric analysis, or like a finite element. And I'm not going to go into this. Zane is going to cover that here in a few minutes, so I'm just going to kind of skip over that. But I just want to bring up, so this is kind of a weird, I think it's a little weird, but it's a home, it's 2,500 square feet, and this is just the initial brush through of when we start looking at it. But you've got to remember that if you're new to shells, or if you're designing or analyzing a shell that you don't know a lot about, and you put it in a finite element, you might not know enough to know whether the answers are right. Okay? And that's dangerous. That's what we don't want. Okay? And so if you have a piece of the shell, you've got a nice dome roof part there, and if you can compare that with a closed form solution and say, okay, look, it looks like it's behaving like it says it should. Now you have some more confidence and you can go through that. And Zane's going to talk specifically on some tricks and what we need to do there. So I'm not going to steal his thunder. Besides, he's smarter than me. So as we're analyzing our shell, we want to look at the supporting members. Okay? They have a huge effect on how our shell reacts. So if we look at this, so right here on the back side of this shell, you've got lots of supports. And so this is a very stiff side over here, okay? Your shell's coming in. But on the front, this is a hanger, so you've got really long spans here. This portion of the shell, this edge member, is going to be very flexible, just based on the span and everything. So knowing that, you have to include that in your analysis of your shell, or it's not going to behave like you think it is. If you just give it some fixed points, and they're not really fixed, it's going to behave a lot different than your assumptions are made. And shells, that's really exacerbated in shells because they're so thin and they span such a long distance. Stability. So most of the time when we're doing concrete design, how much time do we spend on stability? If you're designing a concrete beam, how much time would you look at stability in that beam? Zero. Yeah, that's right. That much time, right? Well, stability is one of the the number one thing that we kind of look at here with shells. They are so thin and they're so they span large distances. So stability becomes a huge factor in analysis and design. So some of the things that we need to look at. So we're always investigating them for stability. So deflections. We can have a large reduction in our shell capacity, when we have deflections, be it dead or live load deflections, or creep effects. Now, talking about a concrete dome, the very top of that is generally all in compression. And so, depending on the level of compression, the stress in there, we can have lots of creep, so we want to minimize that, so we have less creep. The more it creeps, then the top deflects, right? And so then the radius of curvature gets longer, and that makes our stability go down. Cracking, we design concrete cracks, right? That's what we know that. That's how we design it. We design concrete so that it will crack in the right spots. And so we'll see the cracks, and then when the cracks get big, then we know that, hey, we've got a problem, or if they stay small, we don't have a problem. Well, shell structures, as in the tensile zones, as it cracks, then we lose some thickness of our member, and so we have so it's not as, we lose some of the modulus of elasticity, so that all of a sudden it's the buckling and the stability goes down. So we need to be really careful of that. And then the engineers always think that everything we design is built exactly right in the field, right? If we say it's this tolerance and this, then that's exactly what gets built. Well, that doesn't always happen. And so we have to remember that there's a deviation, and hopefully we have, when our stuff's in construction, or we know who's building and what's going on, that we can take that and use that, knowing that in our analysis, what we're going to do with that shell. So items also that affect buckling strength, thickness and span, we've talked kind of about that. So everything else being the same, if a shell spans a certain length and it's a certain thickness, and you increase the length, then the buckling capacity diminishes. Same thing if you have this length and the thickness goes down, then the buckling capacity diminishes. So that's probably the greatest thing that affects the shell stability. Second is supports. So we go back to that hanger. That one support is very flexible. If it moves out, what happens to our shell? Well, the top comes down. So we've increased the dimensions again. So then we're back to thickness and span. We're increasing the span or the effective span. So that can really affect the stability. Loading is is not really as much. Usually shells, especially shells in double curvature, they take external loads very well, uniform loads. Okay, they can resolve those loads very well. However, when we have our edges, that's where we get discontinuities in the shell, openings or the terminus of the shell at the foundation or other places. That's where we get lots of bending, and so we need to be aware of that. And but for loading, so that's where our bending comes from. But if we put a big point load on a shell, then that is not accounted for in our membrane solution and other things. So we have to understand that a big point load is going to introduce big moments into parts of the shell that were never really designed for moments. And so we have to figure out how to resolve those. So our design of shells, we've used ASD design forever. Now, ASD is a dinosaur in concrete design and analysis, right? When was the last time, who knows, when was the last time ASD appeared in ACI 318? It was in Appendix A. Anybody know? It was sometime in the 70s. Okay? So a long time ago, right? So, but why? So why would we still use it? Well, because we don't design shells most of the time. We don't design shells based on strength. We design shells for this. I mean, the strength is fine in a lot of things, but we have to design them for stability and other deflections and things. And so we want our stresses to be very low. And so that's why we look at enough ASD design. That's why it's a good check that our allowable our stresses are very low, just like they were during the ASD period. Okay. If you all shells are the shell chapter or the shell book, as it were. So in 318, we got kicked out of 318 in the 318-14 edition. So apparently all 16 pages of the shell code was too much to add to 318, especially now that it's mostly digital. It's a lot of extra paperwork. So now we're in 318.2. So the good news is that it's a free download. Anyone can get it. You don't even have to be a member of ACI. You can go to concrete.org and you can download 318.2. The bad news for us is it's free, so they don't even feel like it's worth anything. I guess what we do here is not worth anybody's money. So some of the things during design, some of the things we look at are limitations on materials. So in the 318.2 and through the 334.1 document, talks about grade 60 is the maximum that we can use for our steel. Okay, and there's an asterisk, and we'll talk about that. But the reason for that is because strength it's not a strength problem. Okay, so we don't want to use strength out to the very end, but we want to limit that tensile stress. We want to limit the cracking, even more than normal structures. Okay, and so there are some structures we like dome silos where they'll put 50,000 tons of Portland cement or coal or grain or something, right? There are parts of those structures where we can use up to 80 KSI steel, which is specified or allowed by ACI 313 and 350. But for a typical architectural type shell, then we would never use anything greater than the 60 KSI steel. And then concrete strength, it says in there we need 3,000 PSI minimum for shell structures. And it only goes up from there. Like many of our air-plated shells, they use shotcrete to build those, and the ACI 5 or 6 says, hey, you got to use 4,000 PSI minimum. So those are kind of our materials. Stability. Now we're back to design. The main focus of our design goes back to stability, and we won't berate all of these things again. But we need to look at deflections, daily live load, and creep effects, cracks, shell surface deviation, supporting members. All of those things go into our design of how this goes together. So if there's one thing that you take away from this today, it is that stability needs to be analyzed, needs to be thought about, needs to be at the forefront of your design when you're doing a shell structure. Okay? We'll talk a little bit about minimum thickness. So if you're designing a beam, how do you get the minimum thickness? You can look at, for this span, we have to have a certain thickness, or else we have to calculate deflections, right? So, or we need this much depth to put our steel in to get the strength up. Okay, so it's pretty straightforward. For shells, our minimum thickness could depend on a lot of different things. Okay, so one of the most common things is just how much concrete do we need to cover our steel. So maybe we have a shell and it only needs to be by analysis for strength, and then it only needs to be an inch thick. But we're going to put two mats of numbers, or we're going to put a mat of number 4 bar each way, right, crossing. So you got half inch. So you got 1 inch of steel in there, and you got to have a half inch of coverage if it's not exposed to earth or weather. That's the minimum shell coverage. So you get half inch and a half inch top. So now 2 inches. So now instead of saying, oh, I only need an inch for strength, you need 2 inches because of just your concrete cover requirements. Sometimes the attachments to your shell might be make the required minimum thickness. So if you're going to put a wedge anchor into some concrete, can you do that in 2 inches of concrete? very difficult to make a wedge anchor work and attach something to a shell. So now all of a sudden your shell might be 4 inches or 5 inches thick just because of what you need to attach to it. Maybe it's a cover over a basketball arena, and you need to put a scoreboard up on the top, right? And you for strength and for stability, you only need 3 inches of concrete, but for attachment, and then you might need 4 or 5 inches of concrete to make that work. So all of a sudden, our minimum thickness can jump around based on different things that aren't necessarily strength, and that's what we normally look at. So that's why I want to point that. And then stability is the other one, right? So if we don't have appropriate buckling capacity, then we need to take those appropriate steps. So our minimum thickness can vary quite a bit by other means rather than just strength. So we talk about compressive stresses. We want to keep them low. Tensile stresses, they're obviously, we resist them entirely by the steel, but we also have requirements in there that the spacing of our bar has to be tighter than a normal concrete structure because the cracking is very critical. Lap lengths. So the specified lap length right here is 20% greater than your calculated lap length. And that's because your shell is twisting. It can twist and turn. So you've got a straight piece of steel, and then it's twisting over here. So if they say, well, you know what? If you've got 20% longer, if you specify 20% longer lap, then you'll get that. You'll get the actual lap, no matter what the geometry is. So you want to look at that. If you just specify what the lap is, and because of curvature, you can't get that, then that's why we specify greater lap. And then shells are really critical where we have splices. Okay, splices need to be staggered, and the reason for that is how do we get the stress out of one piece of steel into the other? Well, it goes into the concrete through shearing, and then into the other piece of steel. And so our shells are very thin, and if we have all of our splices stacked up in the same space, then the shear stresses within the concrete get very high. And so we want to stagger those, only 30% in any location so that we can reduce that shear stress in the concrete. Because we don't have a foot of concrete to transfer those through. It might be 3 or 4 inches of shell, right? So we want to reduce those. And then sometimes at the openings or at the edge of the shell, then we can't stagger those slices because you're at a hard edge. So now we just increase the length by 50 or 70%. And that does the same thing. It just increases that zone out further and decreases the shearing stress in your concrete. And then construction of shells. We have a lot of shells, different types of shells that use hard forming. This is a dome that has an air form, and there's spring shotcrete here. So during construction, we leave that to the contractor. But once again, it's something that if you have hard forming and it's an arch, and they're going to decentering it, they've got to make sure that they counsel with the engineer and the designer, because that could, your decentering forces, depending on where you take the posts out and what you do, those could be higher than your shell stresses in the end. So those type of things, how it's going to be constructed, how they're going to do that needs to be considered by the designer and worked out with the contractor during construction. So, all right, that's all I have.
Excellent.
Thank you.
So, thank you.